Um, we will present this both here and in Detroit, and then this entire report is also available on a white paper that we posted, and I will point that to you at the end of the presentation. So, goal for the presentation is to answer these 5 questions. First, who are we? And more specifically for today, who am I? Why did we do this? What did we do? What were our results? And then what did we do with this information? That's one of the first questions that we get when we talk to people about the testing was, okay, you did this in the fall. What did you actually do this season? How did you implement that? And so we'll go over a little bit about what our 2018 robot incorporated from this 2017 testing. So first, a little bit about us and me. My name is Colin Foltz. I started in first robotics competition as a student on Team 234 in 2002. I have a mechanical engineering degree from Purdue University, and I have the honor of working as a first staff member. I worked for first robotics competition from 2010 to 2015 and was able to serve on a few game design committees in there, and I currently work for the first Lego League Junior program. And I also mentor Cyber Blue Team 234. We started in 1999. We're located in Indianapolis, Indiana, Perry Meridian High School. We are a co-host of the Indiana Robotics Invitational. It takes place every summer. And then we host at our facility the Indy Rage, which is an all-girls event we host each fall. We've been doing that for 3 years, I believe. And then we do publish quite a few test papers and other reports available on our website. We post them on Chief Delphi. 2009, we did a belt versus chain analysis and really tried to understand which was better to use in an FRC drivetrain. We did a swerve drive development, co-partnered with a company called 221 Systems, and helped them do some development on a off-the-shelf swerve module that they were designing. We've posted a lot of information on our design review process that we go through throughout the competition season. And then our business and sustainability plans, how we interact with our sponsors, our team equity plans, all of that stuff is available on our website as well. So the technical and the non-technical side is available. So why did we do this? Anybody that was in first 2013 or before remembers the days of only 4 sims allowed on our robots, and those were really the high power motors available. Other motors came and went throughout the year. You can come on in and grab a seat. You're not gonna, it's much more comfortable in a chair than on the floor. You're not gonna bother me. That was really what we had, and so the common wisdom, the conventional wisdom was you put those motors in your drivetrain and you're done. A number of suppliers had come up developing off-the-shelf gearboxes that worked for those 4 sims, and that was the standard. In 2013, that number bumped up to 6, and Vex introduced their mini sim motors, and up to 4 of those were allowed on the robot as well. 2015, number of sims stayed at 6, and this time, at this point, the mini sims became unlimited. You could use as many as you want on your robot. 2016, number of sims stays the same, mini sim stays unlimited, and West Coast Products introduces the 775 Pro motor, and again, unlimited number theoretically available on your robot. Now, it really becomes up to you to manage your power consumption. Pre-2013, first didn't give us a lot of rope to, to hang ourselves with. That the doors started to be opened a little bit, and then this year, 2018, unlimited motors, use whatever you want. If you kill your battery every match, that's on you. And so it really became important that people understood their power consumption, especially when it came to how you design your drivetrain. Along with those rule changes, there were a couple of really successful robots that helped kind of spur the innovation. The first one that at least sticks out in my mind, the Cheesy Poof's 2014 robot, world champion robot, and it used a 6-sim drive. And then this past year, Team 2451 used an 8 775 Pro gearbox, custom designed, and used 8 775 Pros in their robot. They actually started with 10, and through testing was able to work themselves back to 8. And as you saw, they had 2 regional wins here. So a couple of teams that pushed the limits on gearbox design, that did things a little differently and had really great success. Now, the question becomes, were the robots successful because they had these different drivetrains, or were these different drivetrains successful because they were implemented by teams that usually have success with their robots? And which came first here? And so we wanted to try and challenge some of the conventional wisdom and go back and actually do the testing, to do the math. So we wanted to test the following statements. And again, this is kind of that conventional wisdom, the anecdotes that you see thrown about. The first is that just putting more motors on your robot automatically gives you faster acceleration. That there's a limited amount of power that you can pull at any point, and that one motor can pull, but if you add more motors, you will accelerate faster. You may not change your top speed, but you'll get there earlier. The second is that, we only use sims in our drivetrain. We only use mini sims. We only use 775s. So we wanted to see what are the best, what are the strengths and weaknesses of both. And then the other comment of, we will never draft a team that has a 775 Pro drivetrain, they're too risky. And so we wanted to actually, see how risky they were. We also, so Bill Beatty is a Championship Woody Flowers Award winner and was the lead design mentor on Team 71, Team Hammond, the only team to win 4 world championships. And according to Bill Beatty, there are 3 most important parts of the robot. Can anybody guess what number 1 is? Bingo, the drivetrain. Can anybody guess what number 2 is? It's also the drivetrain. And what about number 3? It is the drivetrain. If you can't move, it's really hard to do anything else. So your drivetrain needs to be the most robust part of your robot. And that is really agnostic of the game. He gave a presentation on that in the early 2000s and was saying it then, and that's held steady until then, or through today. So what did we do? The first thing, if you want to test a chassis, is you need to make a chassis. And so we wanted to build a very basic chassis that allowed the drive motors to be changed with no other changes to the robot. So using a design of experiments methodology and philosophy where you only change the item that you're testing. So swapping out from a gearbox that was designed for Sims to a gearbox that was designed for 775s wouldn't have worked for us, because then we're also having to account for the changes to the gearbox. So we wanted to make sure that we were only testing the motors. Also, we wanted the ability to maintain the overall robot weight. 775 motors weigh a lot less than the Sims, and a 775 gearbox weighs a lot less than a Sim gearbox of comparable power. But we didn't want the changes in those weights to impact the overall testing. So we wanted to make sure we had a way to maintain a consistent robot weight. We had also heard, and some people thought that you could start introducing a lot of wheel slippage during acceleration, that even though you had the power to accelerate really quickly, you weren't actually accelerating that quickly because your wheels were just spinning and burning out before you got going. So we wanted an idler wheel that we would use to track the true robot travel distance, and then compare that to what the driven wheels thought that they were going. We wanted to use an FRC legal control system because we wanted this to be applicable to this year's FRC season. And then also, we didn't want to rely on a human operator, and that human operator making sure that he or she was driving the robot the same way as they did yesterday or last week or 2 months ago. We were going to do this a couple hours a week, over the course of 2 or 3 months, and so we wanted to make sure that the way the robot was driving was the same every time as well. So this is the robot that we designed. Pretty standard West Coast drive, 6 sim, 4-inch Andy Mark high grip wheels, direct driven from a Vex 3 sim, or a West Coast Products, 3 sim shifting gearbox, 25 chain to the front and back wheels. You can see the FRC control system on there. We did put bumpers on the front and back because we were testing in our school and testing with an autonomous program, and so if it ran into something in the hallway, we didn't want to damage the school. And then we built that aluminum structure on the top that we put a plastic tray in that we would add weight to, plate weight and dumbbells to to get the weight up to about 135 pounds for each test. After we had our test chassis, we had to start thinking about our test protocol. How were we actually going to ensure that the only things that we were testing were the motors? So we ran all of our tests in the same area of the school. We ran all of the tests in the exact same order, and we started each set of tests with a battery right off the charger. So that way, test number 9 was always getting a battery that had been through the same number of cycles and accelerations as you know, for each test configuration. In addition to downloading and checking the data after each test, we also had a human taking notes, and we made a form for that person to fill out that had the robot weight, the motor configuration, and then what we had named each of the files, and any notes that the you know, that the person wanted to write down, so that we could go back and say, oh, I think we noticed that last time as well, let's check that. So that was helpful, just to have that extra paper copy in addition to all the data. Then we started thinking about our testing sequence. We ran 12 configurations total. Come on in, no worries. So we started off with the basic, and the other thing we tried to do here was limit the changes test to test. So like once we got into the 775s, we wanted to stick with them for as long as we could. So we started with 4 sims, then we added 2 more. We took those 2 off and put the 2 mini sims on. Then, because we were going to an off-season event, and we wanted to test what we had done on the robot so far in an actual competitive environment, we actually took all the sims off and put the 775s in their place, and then used that for the boiler bot battle, switching between using 8 775s and 6 775s and capping their maximum voltage at 80% there. But then we gave our driver the opportunity to go out, and we really didn't have any significant issues there, but the robot was just a basic gear robot with a climber on it, so it was pretty light and not really taxing the robot. The other thing that I should say about the 775 motors, in order to make them fit into the sim input on those West Coast Products gearboxes, we had to run them through a versaplanetary gearbox. So it put 775 into a versaplanetary 3-to-1 with a sim output shaft, and that made it so that they mounted right on there. At the time when we conceived of this test, which was actually driving home from St. Louis last year, and when we were doing this test, there were no commercial off-the-shelf 775 drive gearboxes. Andy Mark has since come out with those. At the time, those didn't exist, and so we wanted to kind of approach this test from the perspective of a team that doesn't have the resources to make their own drive gearboxes or to design their own. So we wanted to stick with off-the-shelf components. And so that's noted in our report and is something that we've talked about evaluating next year, is actually designing or using one of the Andy Mark gearboxes, but something specific for 775s. After the 775s, we switched to pure mini sims, 6 and then 4, and then since we had taken the mini sims off, we wanted to add some sims in, and then just to get a complete baseline, we stripped everything away and ran one of our tests with only 2 sims to see maybe we've all been crazy this whole time and the robots would have been fine just running with 2 sims, in which case you save a lot of weight, potentially save a lot of money, and could use motors elsewhere. Oops. So this is our test sequence. The first test was just to put the robot up on blocks and run the motors full speed forward for 10 seconds. This did 2 things for us. The first was it gave us kind of a baseline performance of the current that the motors were pulling in what could be construed as a free speed. It also showed us if we had anything wired backwards or if we had a bad battery, because we were able to compare a number of encoder counts of how far we thought it should go versus how far it actually went. We could use it as a bit of a test before we put the robot on the floor and make any changes. This came in really handy when we went to test the 775 motors, and we actually flipped the electrical inputs on 2 of them and the robot immediately started having problems. Because it was on blocks, we were able to figure that out. Yes? That was on high gear, yeah. Yeah, because our first set of tests were in high, we just put it in high there. Second test, we went out in the hallway of a school, put it on the floor, and 50 feet, dead sprint in high. One of the things that we realized as we went through the testing, when we went from test 1, which was the 4 sims, to test 2, which was the 6 sims, was we were going from 0 to 100% power in one cycle of the code, so approximately 20 milliseconds. This was causing the robot to brown out, and that got really bad when we went to 6 sims. And so we did some testing with our human driver to see how fast he was actually speeding up and slowing down and changing directions, and we built those ramps into the autonomous code so that even though it was running autonomously, it was mimicking closer what an actual human. And we figured out that it took him about 13 cycles, or about a quarter second, for him to move the joystick and the joystick to register him telling the robot to go forward. And that really came in handy on the test number 4, where we went 50 feet in high, stopped, and reversed. The first time we tried to do this with 6 sims, we went 50 feet in high again, and then again in one cycle, so 20 milliseconds, went from 100% power to negative 100% power, and the robot just turned off because it pulled so much current through. So we put that ramp in, and then we didn't have any problems throughout the rest of the test on any configuration, and we stuck with that because we wanted to maintain that autonomous program. We stuck with that regardless of whether we thought we needed it. We probably could have taken it out when we got down to 4 mini sims, but for the sake of consistency, we kept it in. About a quarter second, yeah. So our second test, we went forward in low gear and then did the remainder of the 50 feet in high gear. And again, this 50 feet was based on measurements from the idler wheel. So that extra 4-inch wheel that was at the middle of the robot and had a spring on it to make sure it stayed in contact with the floor. We used the encoder on it and then compared to the encoders on the drive wheels to see if we were seeing any slip. We did 50 feet in low, which if you've ever driven a robot designed for 10 feet a second, 50 feet in low gear, that's painful to watch. And then the test that I really liked, that I thought was the closest to what an actual FRC game could entail, and was actually pretty apt for this year's game. The robot went forward 10 feet, turned right 90 degrees, went 10 feet, turned left 90 degrees, and then another 10 feet and stopped. So that's kind of that quick acceleration, stop, turn, move, stop, turn, and because we wanted to get one that wasn't just a drag race. We did pushes against a wall. We tried to do the same spot in the school, but we started burning up the carpet, so we had to move side to side a little bit. It was a dimly lit area, so we don't think our principal knows that it's there, but there are 6 burn marks on the floor. And we did a voltage ramp there as well, where we started at 0% power and over that 10 seconds ramped to 100%. And we wanted to see at what point, at what input do the wheels break free and start spinning on the carpet, or do they never break free and you're always current limiting your drive motor based on which motors that you pick. And the big thing there with all these tests, one of the things we wanted to do was compare our actual results to the results that come out of the various calculators and simulators that exist that teams use to see, okay, how real are the parameters that are being input there? How real are they in actually predicting what your robot will do? And so that pushing speed or that pushing power available is a big one that I think teams look at. We certainly look at a lot. When you're going through and actually designing your robot, because we at least like to make sure that we're traction limited, especially in low gear if we're doing any shifting. So what were our results? The first big one was that most of the tests were just fine. They were relatively the same, and I've got a couple of charts that show that, and that all configurations could be made to be suitable for most FRC drivetrains. If you are trying to do something very specific, or if the game requires something specific, then certain configurations may be better than others. But any of the motor combinations that we tested based on our testing would be fine. The 2-sim, we only tested that test 2. Looking back now, I wish we would have gone through the other tests on it, because I think especially the stop and reverse, that would have taken a lot longer. And that's anecdotally, that's what we've seen too, is that especially in turning, you just don't have enough power to overcome the scrub. We saw a very minimal difference in acceleration, total top speed, and a time to a certain distance, and even slicing up that distance. So, okay, what about just the first 10 feet, just the first 20 feet? Is one faster or slower? And they are, but it's by, fractions of seconds. Surprisingly to us, we didn't show a significant amount of wheel slip in any configuration. That stop to a full speed start obviously showed some, but the pure acceleration, from a stop at the start of the test didn't show really any wheel slip. And then, like I said, the 6-sim and the 775 Pro did have brownouts during the sudden starts and stops, but that voltage ramp that we implemented got rid of those, and we didn't see any other issues. This is one of our tests, the plots from it, and I've taken out, I've only shown what I feel like are the 4 most common drivetrain motor configurations, the ones that probably teams use the most. And this is our 50-foot down and back, and I apologize for the end of the chart where we lost some of the data. But you can see, that time to the 50 foot distance, which is about 14,000 encoder counts, was basically the same, and then extrapolated out. We might have saved a half a second over 100 feet of a drag race there, but generally they were about the same. The next one is our turns test. So this one is interesting because the 4-sim actually shows as starting to be faster. We're not really sure why that happened, but in this test, the motor configuration that just used the 4-sims was the faster of the 4. So some of the things that we didn't account for in this, like I said, we use the exact same gearbox for all of these testings, so we didn't optimize for a specific motor combination like you would do if you were designing your robot and said, we know we want to use 6 sims. You could design it a little bit differently than if you said we're only going to use 4. We also didn't optimize the control logic for a specific motor and gearbox combination. We could have spent time going through and saying, okay, for the sims, we need the voltage ramp to be a quarter of a second, but for the 775s, it can only be 200 milliseconds. We didn't do that because we wanted to focus on maintaining that control over the test. And then the big thing that we didn't do that most impacted our decision making going into the season is that we didn't really simulate a full match or back-to-back matches for that impact on the motor performance. If you look at all the testing that we did, even putting all the time together, you maybe get one match over, it typically took us about a half hour or 45 minutes to run all the tests. So that wear and tear on the motors, we just weren't seeing. We also used brand new motors at the start. So the sims that we put on were fresh out of the box, and they saw, over the course of the testing, maybe 4 matches worth of actual time being used. And if you think about where the stress in the motor really comes, the start and the stop, reversing, just because of the way the tests were designed, they didn't get a lot of that wear and tear. So what do we do? When we first saw the game, we immediately jumped to comparing 4 sims to 6 mini sims. Looking at these, there was a comparable nominal power available if you look at just total wattage that's available from the motors. We thought that the four sims are lighter than 6 sims. They also would cost us less, which is good. They use fewer motor controllers, fewer PDP slots. The gearbox could be a little bit lighter, and like I said, use fewer motor controllers. One of the things that we thought was really important was that the 6 mini sims could allow our robot to be a little narrower just because they're shorter, or could open up space in the middle of the robot. And at the beginning of the season, when we're thinking about ways to buddy climb or lift a partner or do something like that, and we're thinking we may need some of that space in the middle of the robot, the mini sims, that part of the mini sims were a benefit for us. In the end, we chose to go with a 6 mini sim ball shifting gearbox. We chose the Vex ball shifters for this one. There were a few things that we liked about them for this year's game. And the reasons that we chose those was that while the 2 sets of motors that we identified have comparable nominal power, the testing over a 3-minute period from that was done by Vex shows a significant total power drop-off for the sims versus the mini sims, and that has to do with where the mini sims are designed to operate. They're really at max power. They're at 40 amps, which is perfect for FRC. Like I said, they're designed to run at max power at 40 amps, so we're less likely to be tripping the individual PDP slot breakers if we were to get into a high current situation. And then the big thing that we liked for the mini sims versus going to a 775 drive, because at our off-season event we had good experience with the 775 drive, was that say our testing was way off and all of a sudden we start having trouble with the mini sims or with the 775s, it's really easy to switch back to a 4 sim drivetrain from a 6 mini sim drivetrain. Much easier than it is to rip out a custom 775 gearbox and put in a sim one. You're sacrificing then a lot of weight that hopefully you've accounted for somewhere, whereas 4 sims are actually lighter than 6 mini sims. So it was also potential weight savings for us. So if we get into this position where we really need 1.5 pounds or 2 pounds, we know we can get it back from the drivetrain with maybe just a little bit of performance, performance impact. This is the Vex data that I was referring to. So as you can see, the time here, whereas ours were maybe 9 seconds maximum, this is actually 180 seconds, so 3 minutes. And this is comparing total power available from 4 sims versus 6 mini sims. So on a motor per motor basis, the sims don't have as much, but when you put 6 of them together compared to 4 sims, that you maintain that maximum power for a lot longer. And then anecdotally, we had heard, in terms of back-to-back matches, the motors don't get as hot as the sim motors do. And so that will be helpful as well, coming from a team that plays in districts, where often we are coming off the field and immediately getting back in the queue because we have a match, every third match, or in an elimination, the playoff situation, we want to make sure that our drivetrain is operating at peak performance there. So that's what I had. The reason that we did the test and the reason that we published all of our data, and our full test report and data set are available on our website, cyberblue234.com. If you click on resources, I believe it's the top right corner, and white papers, it's there. There's also a link where you can download a zip file of the raw Excel data from every single one of our tests, and the white paper gives you the naming convention so you know which test you're opening at which time. The reason we posted all of that is that we would love for a team to try to replicate the test, right? That's kind of the pure scientific side of this, is if somebody else can replicate a test and get your same results, then you did a good test there. And so we would love it. The robot was pretty simple. The autonomous codes are pretty simple, and we'd love to talk with you if you're interested in doing this. For us, it was a nice project to get our newer members more involved. It got our autonomous team, our controls team thinking about new ways to control the robot and how we would get that data. And so it was a nice team building activity for us in the fall. And then also just check our numbers, check and see what we got versus what you got and see if it makes sense. And then if you've got other questions, there is about a 3-page thread on Chief Delphi where we also posted the white papers. If you search for white papers by Chris Foltz, it will show up there. And so we answered a lot of questions in there. If you have questions and if you post to there, if it's something that you think everybody could benefit from seeing, we will respond to those questions. And then if you just got other general questions about what we did or how you could implement it, my email address is colinfoltz@gmail.com. Feel free to reach out and ask, and we'll get back to you. So with that, I think that's my last slide, so I will take any questions. Yeah.
Could you go back to the graph before, just with the stop start? Is the one that did it the lowest time 6 mini-sim?
Yes, yeah, so this is the 6 mini, sorry, the colors are a bit wonky. The 6 mini-sim, 775, 6-sim, and 4-sim here. Yes? A voltage ramp, so instead of going from 0% power to 100% power immediately, we set our code to do it over the course of a certain number of seconds. And in our case, it was a quarter of a second, 250 milliseconds. Yes? We did not use motion profiling. We don't have experience with that, unfortunately, and so we didn't use that.
How did the different drivetrains compare for the pushing power?
Yeah, great question. I did not include. I didn't include that, and these are in our in the report. We give the results for all of these. They performed, I guess, exactly as you would think they would. In low gear, all of them were traction limited at full power. The 6-sim, the 4-sim plus 2 mini-sim, the 8775, and the 6 mini-sim were also traction limited, I believe, in high gear. And then the others continued to stall the motors in high gear. They never, the wheels never broke free. So, and all that's in our test report as well, the specifics there, and that the specific data is available in the Excel files. Any other questions? All right, well, thank you all very much. And I'll stick around if you want to come up and ask anything else specifically, and if not, good luck this weekend.